Hello, my name is Brian Dick. I'm a software engineer, and this is my YouTube tutorial series on the HackerRank interview preparation kit. We're currently going over sorting, and this is the merge sort counting inversions problem. It's rated difficulty hard, and it has a 54% pass rate. In an array R, the elements at indices I and j, where I is greater than j, form an inversion if R sub I is greater than R sub j. In other words, inverted elements R, R sub I, and R sub j are considered to be out of order. To correct an inversion, we can swap the adjacent elements. For example, we have R of 2, 4 equal to 2, 4, 1. To sort the array, we must perform the following two swaps to correct the inversions. R is equal to 2, 4, 1. And then we take the swap of the element at 1, so 4, and the element at 2, so 1. We swap those two. And then we swap 0 and 1, which will now be this 1, to give us 1, 2, and 4. The sort has two inversions, 4 and 1 and 2 and 1. Given an array R, return the number of inversions to sort the array. Function description: complete a function count inversions in the editor below. Count inversions has the following parameters: int r sub n, an array of integers to sort. Int is the number of inversions, is what it returns. Okay, so basically what we're trying to do here is we want to create a function that is able to count the number of swaps that take place in order to sort this array, right? So we're basically going to be, as the name of the problem implies, performing merge sort and then simply counting the number of times we invert the indices. So we are taking from the right side instead of the left side in the merging process. So first of all, for those of you that don't know, merge sort is probably one of the most popular sorting algorithms. It's of n log n complexity, so it's quite efficient for a sorting algorithm. And essentially what it does is it breaks down the problem into the smallest possible subproblem. So it starts off by taking this array and then it'll cut it in half. So like for it might take 2 and 1 and then break up the other half as 3, 1, 2. Then it would break that up to just 2 and just 1, and then this side it might break up to just 3 and then 1 and 2, and then break up that 1 and 2 further to just 1 and 2, where they're each their own separate sub-array. From there, what it does is it starts to do the merge process. So it would be merging the array of just 2 with the array of just 1, and then we compare all of the indices as it goes through and look to see if the left side is less than or equal to the right side. If it's less than or equal to, then we're fine. We're still in order, so no swaps have to be made, and we just put it in and merge those two together. So we'd end up with the new subarray. And then it would go all the way back up to the full array, at which point, after that final merge, it would be perfectly sorted. This will always give us the proper number of swaps that occur if we were to do it the way that they show up here. So I hope that is a good enough explanation of merge sort. If not, we're about to implement it, so we will be fine. Okay, so here's our function that we need to implement, count inversions. It takes in a vector of ints called r. So what we're going to do is we're going to, just as merge sort would, we're going to create a recursive function. So we're just going to say that we're going to return from this recursive function that we'll just call count inversions rec for recursive. And this function is going to take in a few things. First, it's going to want the actual pointer to the array. That way, when we make a change to the array, as we're making these subarrays, we end up with the actual array, and that when we're manipulating it, we're not having a copy of the array. We want the actual pointer to this specific array. That way, A, we're not copying the array over and over again, and B, it just makes the implementation a little bit cleaner. So we're going to put in ampersand array, and then, so that gives us that pointer to this array. The next thing that we need is we're going to put in an integer that represents the smallest possible index for this array. Currently, since this is a fresh array, the smallest possible index would be 0, of course. And then we also want the largest valid one, which would be r.size -1. So that'd be the final the leftmost index, if you will. So let's go up here, and we're going to go ahead and create the header for this. So we'll call it long count inversions, and recursive. And we're going to want a vector of type int address called R. No, that's not what we want. We want a pointer. Derp. Okay, so we're going to want a pointer R, an int left bound. So this is the leftmost index. Or let's just call it the left start. We'll call it that, left start. And we'll call the other int right end. So we have our left start, which is the very first index, our right end, our very last index, and then we can go ahead and we're going to count up the number of inversions. Num inversions, and we're going to initialize that to 0. Then we're going to check, we're going to say if the left start is greater than or equal to our right end, then we're going to just simply return 0, because we don't want to do anything. We don't have anything in merge. This means that we have that subarray of just size 1. So we're done with this recursive action of breaking down that array smaller and smaller. We are now currently at an array of size 1 effectively. Okay, so now we're going to say int mid, the middle, is equal to the floor of the left start plus the right end divided by 2, like so. So this is just going to give us the middle index of this subarray that we'll be creating. And then we're going to do the recursive call. So you're going to want to continue to break this down further, and we're going to count the return. So num inversions is equal to the count inversions rec. Oh, shoot. Didn't want to do that, but whatever. And we can just pass in array. We can pass in our left start and then our middle, so our midpoint. And then we're going to want to do num inversions plus equals the count inversions rec. I wish it had a better auto than that, but whatever. And this one we're going to be starting at mid plus 1 because these are inclusive indices. So the first one includes mid, so we need the next one after mid, and then a right end. So this will be that second half of the subarray. And then we're going to finally create another helper method that's going to bring everything together. That is going to be called merge. So we're going to say num inversions plus equal merge. So at the very end, once we come back from all these recursive calls, we'll be getting the return value will be this merge, which then will have the proper array at the very end. So we're going to put in R. We're going to put in our left bound, our mid, and our left start, our mid, and our right end. So this will give us all three. This will give us all the information we need to break out the subarrays, so we know where in this original array the subarrays that are being merged exist. If that makes sense. It'll make more sense as we do this next step. And then finally, we just simply return num inversions for the recursive call to continue working its way back up until we have the final original call that was made in countInversions. Okay, So now let's create this merge function. So we're going to want a merge, and this one is going to be pretty similar to the other. We have merge. It's going to be taking in a vector of int pointer called r. It's going to take in a int left start, an int mid, and an int right end. And then we are going to be creating a long num inversions, just like before. We're going to initialize that to 0. We are then going to say our int left array size, because we're going to create 2 subarrays here, is equal to the mid minus the left start. So wherever the middle of this subarray is from the bigger picture, the whole array, we're going to subtract wherever the start of this. So let's say that our starting point is like we have a subarray. Like let's just do something stupid simple. Obviously not hard to sort this, but just to give a visualization. So let's say this is our whole array that R is pointing to. We might have a left start of our second index, a mid of our third index, and a right end of our fourth index, for example. So in this case, what would happen is we take the where is it? Oops, wrong function. Oh well, we'd be taking that mid, which would be the value here, subtracting, which would be in this case 3, subtracting from that 2, which would give us 1. So the size of the subarray would be 1. It would just be, it would just be that first element. And then the other subarray is going to be, we can add 1 to that, and that'll give us the first one. So if we add 1 to that, that would give us the first one, and then the second element here. That way we'd have a size 2. And then the other one would just be this, which would be the right end subtracted from the midpoint, which would be 4 minus 3, which gives us size of 1. You could do that the other way around, whichever side you want to be bigger. It doesn't really make a difference. But this is how we're going to implement it. So we'll do int right array size is equal to right and minus mid. There we go. Okay, so now we're going to actually create these 2 vectors. So vector, and this is just saving us the hassle of doing ints. There's many different ways you can implement merge sort. This is just how we're doing it. They're going to initialize this to left array size and vector of int right array, and this is going to be right array size. Okay, so those are our 2 temporary vectors, and we're going to do a for loop here. So we're going to say for int I is equal to 0, I is less than the left array size. We're going to do I++, and what we're going to do is we're going to actually build these subarrays. So we're going to say left array at the sub I is equal to the dereferenced pointer to a vector. So now we have the actual vector. I plus the starting point, so wherever the left start is, because this is going to be offset of the original based on where the starting point of the original was. All right, so that's going to build that left array, and then we're going to want to build the right array. So the right array is going to be int I is equal to 0 again. Well, j, sorry. int j is equal to 0. J is less than right array size. And then increment j. So we have that. And then we are going to say our right array at sub j is equal to the dereferenced array again at j plus mid plus 1. Because remember, this array is starting at the middle plus 1 since the indices are inclusive here. And that ties into here. That also ties into down here where we're doing the recursive call. The right array always is starting at mid plus 1. So when we come back and we go to merge them, we're taking this subarray and this subarray, and we're then merging those two subarrays that we create in this recursive call together. So that's the idea here. So we are just reflecting that in the indices for this subarray that we're building for the right side. Okay, so now we have these two subarrays, which are just effectively glorified temp values. We're going to initialize some values here because we're going to create a while loop. So we're going to have a left index is equal to 0. A right index is also equal to 0. We're going to create a int index. This is our quote unquote true index, which is going to be starting as our left index. And this represents the index. So current value from the left side. So that one points to the current value of the left side. Current value from the right side, not side, not size. And then the current index of the real array, the real R. So this is the index of where this is going into that vector that we're pointing to for the big vector that we're actually sorting. So then we're going to create a while loop. It's going to be while the left index is less than left array size, because we don't want to go beyond the bounds that we have for these subarrays. And the right index is less than our right array size. Same reasoning there. And don't want to go outside of that subarray either. We're going to check. We're going to say, we're going to see, hey, is the left array at the current left index, the left array's index, is this less than or equal to the right array index? Or sorry, right array at right index. Boom, like so. So if this is true, then we are going to be just simply placing in the left array value. And that's the correct value. And then we're going to put in at index, the true index, is equal to left array at left index. And this is what would make sense because the left side should always have the smaller value. So no swaps had to occur here. We're good. We just are going to simply increment our left index. Now, if not, this means that our right array's value is less than our left array's value. So we're going to have a swap here. We're going to be taking that right array value, and that means that a swap has occurred. So we're going to want to do first of all, dereference the array and set the value at index equal to not the left array, the right array at the right index. We are then going to increment our right index to make sure we have the right value there. And then we're going to be increasing the num inversions by plus equals the left array size minus the current left index. Now, the reason for this is if we have this subarray and we're having to move, oh, sorry, let me just create one right here. So let's say we have 1, 2 on one subarray and then 1, 3 on another subarray. So when I go to merge these, this is going to be in the correct place, and then we're going to be comparing 2 to the 1. The 2 is obviously greater than the 1, so we have a problem. Well, how do we resolve this problem? What we're going to be doing is we're going to be placing this in front of exactly one element. Cool. But let's say that we had 1, 2, 3, 4, 5 even, okay? So now we are needing to get it in the right place. We are swapping with 1, 2, 3, 4 elements before we get to this right place. So this would be, the left array size is 1, 2, 3, 4, 5. So we have 5 minus the index. Well, the index is 1. So that is a swap. That is a total of 4 swaps that had to occur for it to get to its right place. Does that make sense? So that is what we're doing here. We're emulating that thought process. Of course, these should probably be closer to equal. They might be off by like 1, but usually wouldn't be this drastic. But you could still end up with these subarrays having things really off, which would cause you to have a lot of movement here. Anyway, so that is counting the total number of swaps that occurred on this swap. And then outside of either of the if statements, we are always going to want to increment the index for the original array. Now, we're not quite done yet because this breaks if we hit the end of our left side or the end of the right side. So we need to check to make sure we're at the end of both. So we're going to need 2 more while loops to finish out the left index or the left array or the right array. So we can just start with the left index. So left index is less than left array size. We just lace them all in. And it's worth noting here, we're taking all from one side. So all swaps have already been accounted for. So we've already done all of our inversions for this time around. So we don't need to count any more inversions. We just need to just take what's there, fill it out all the way through, continue to increment the index and the index of the respective array. Okay, so we can basically do the same thing here twice, dereference the vector. Go vector at index is equal to, on the left array, at left index, boom, like so. And then we want to increment index and increment our left index, like so. And we're going to do the exact same thing. So I'm going to commit the sin of copy and paste because all we have to do is do the exact same thing, but replace all of the left with right. So right index less than right array size. Array is equal to right array at right index. And instead of incrementing left, we increment right. So now at the very end of this function, all we're going to do is return the number of inversions that occurred. So return num inversions. And let's see, everyone happy? That looks good. And I think we have everything. So let's go ahead and run code. Make sure everything works. Oh, we got the wrong answer. Okay, I typed in something wrong. So we were expecting to get a 1 and we got a 6. Okay, we did something really bad. Let's see what we did. This is our problem right here. This is not supposed to be left index. This is supposed to be left start. Okay, whoops, typos. Yeah, that would scramble it up instead of sorting. Should be an issue. There we go. Now it passes. And we're going to go ahead and submit this code. Boom. There we go. We have passed. Congratulations. That is how you solve the merge sort counting inversions problem. Sorry for that little typo there. So many lefts and rights here. If you have any questions and need further explanation, please leave your questions in the comment section below. Thank you so much for watching, and until next time, bye-bye.